NASA reports that its Voyager 1 probe, the most distant human-made object in the cosmos, is once again sending valuable information back to Earth. While we are still unsure of its exact nature, we can measure it. Voyager 1, the iconic space probe launched by NASA over 45 years ago, has transmitted a signal that has created a stir within the scientific community. After traveling nearly 14 billion miles from Earth, Voyager 1 has made a discovery so significant that it has changed the direction of its mission, turning back toward our planet. But what exactly could this discovery entail? Could it be evidence of extraterrestrial life, a cosmic anomaly, or something even more astonishing? In this riveting exploration, we will reveal these astonishing findings. Voyager 1 has just made a startling discovery that has prompted it to redirect its course toward Earth. The Voyager twin probes, if not for the alignment of certain celestial events, might never have departed Earth. Around 60 years ago, the 4 largest planets in our solar system were slowly aligning in a way last seen during Thomas Jefferson's presidency in the early 19th century. This rare planetary alignment initially went unnoticed. The first individual to recognize its significance was Gary Flandreau, a doctoral student in aeronautics at the California Institute of Technology in 1965. As space exploration was just beginning, Flandreau, working part-time at NASA's Jet Propulsion Laboratory in Pasadena, California, was tasked with determining the most efficient way to send a space probe to Jupiter or even further out to Saturn, Uranus, or Neptune. Using a simple pencil, he meticulously charted the orbital paths of these giant planets and made a fascinating discovery. In the late 1970s and early 1980s, all 4 planets would align in a way that would allow them to be visited in a single mission. This alignment meant that a spacecraft could use the gravitational pull of each planet to propel itself to the next, significantly reducing travel time. Flandreau calculated that this alignment would cut the flight time from Earth to Neptune from 30 years to just 12 years. However, this planetary alignment occurred only once every 176 years. To take advantage of this rare opportunity, a spacecraft would need to be launched by the mid-1970s. NASA seized this once-in-a-lifetime chance and built 2 spacecraft to undertake the journey. These spacecraft, Voyager 1 and Voyager 2, were launched on an extraordinary mission to explore the outer planets of our solar system. Thanks to the planetary alignment and Gary Flandreau's visionary calculations, the launch of the Voyager twin probes on September 5, 1977, was a historic event at Cape Canaveral in Florida. Voyager 1 embarked on its epic journey into space, propelled by a powerful rocket known as Titan 3E or Centaur. Just 15 days after Voyager 2's launch on August 20, 1977, Voyager 1 began its cosmic adventure, starting its voyage into the vast universe by following a shorter trajectory. Their primary mission was to explore the massive gas giants in our solar system, such as Jupiter and Saturn, along with their numerous moons. However, these daring space travelers exceeded all expectations. They ventured far beyond, pushing the boundaries of exploration and traveling farther and longer than any other spacecraft in history. They set numerous records on their inspiring odyssey, journeying beyond anything created by humans before, even venturing into a region known as interstellar space, a completely uncharted territory within our galaxy. These pioneering spacecraft, Voyager 1 and Voyager 2, are now more than 12 billion miles away from us. Despite their immense distance, they continue to amaze scientists with the remarkable discoveries they make out there. Most recently, they made a discovery so unexpected that it took everyone by surprise. The Voyager twin probes have achieved some truly remarkable feats. Over 40 years ago, they examined the moons of Jupiter and Saturn, which were initially believed to be dull and pockmarked like our moon. These moons turned out to be vibrant hubs of activity. Voyager 2 made history by becoming the first of the twins to fly past Uranus in 1986 and, just 3 years later, zipped past Neptune, an accomplishment unmatched by any other spacecraft. As these spacecraft continued their incredible journey, NASA employed clever strategies to ensure their operational longevity. They deactivated non-essential components, such as spare parts and heaters, to conserve power. This strategy aims to keep the spacecraft functioning smoothly until at least 2030. For the dedicated scientists and engineers who have been part of this extraordinary adventure from its inception, it is a bittersweet mix of emotions. Their hard work has paid off, and just when they thought the Voyager missions were nearing their end, a stunning discovery emerged from the depths of outer space. Decades ago, the Voyager spacecraft amazed researchers by providing the first close-up views of the moons of Jupiter and Saturn. These moons, which astronomers had thought to be dull and heavily cratered like our own moon, turned out to be vibrant worlds. Voyager 1 reached Jupiter in March 1979, just 546 days after its launch. Voyager 2, following a slightly different path, arrived in July of the same year. Both spacecraft were equipped with Vidicon cameras that used filters to capture full-color images. Interestingly, they were designed to be very stable, spinning through space at a rate more than 15 times slower than the hour hand of a clock, which ensured that the images they captured were clear and sharp. During their mission, the Voyagers took more than 33,000 photographs of Jupiter and its moons, each revealing new and fascinating details. For instance, Europa, one of Jupiter's 53 named moons, was found to have a cracked icy crust estimated to be more than 60 meters thick. As the spacecraft departed from the Jupiter system, they received a farewell boost in speed of 35,700 miles per hour from a gravitational slingshot, a crucial maneuver that helped propel them towards interstellar space. At Saturn, the Voyagers went their separate ways. Voyager 1 passed through Saturn's majestic rings, enduring thousands of impacts from tiny dust particles before flying past Titan, a moon enveloped in an orange haze, and heading northward out of the plane of the planets. Voyager 2 continued its solitary journey, reaching Uranus and Neptune in 1986. During its visit to Uranus, Voyager 2 discovered 10 new moons and added the planet to the list of worlds in our solar system with rings. However, Voyager 2's achievements were overshadowed by tragedy. Just 4 days after its closest approach to Uranus, the Space Shuttle Challenger tragically exploded shortly after liftoff, claiming the lives of all 7 crew members, including Krista McAuliffe, a high school teacher from New Hampshire who was set to become the first civilian to travel into space. 3 years later, as Voyager 2 ascended approximately 2,800 miles above Neptune's breathtaking blue methane atmosphere, it encountered the fastest winds ever recorded on any planet in our solar system, reaching velocities of up to 1,000 miles per hour. Neptune's largest moon, Triton, proved to be one of the coldest locations in our cosmic vicinity, with surface temperatures plunging to an astonishing -235 degrees Celsius. The moon's frozen volcanoes were another extraordinary finding, expelling nitrogen gas and fine particles up to 5 miles into its atmosphere. Following Voyager 2's captivating images of Neptune and its moons, both spacecraft were set to deactivate their cameras, marking the end of their official mission. However, astronomer Carl Sagan, a member of the mission's imaging team, intervened. Although the grand tour was officially over, NASA extended the mission with hopes that the Voyagers would venture into interstellar space. Renamed the Voyager Interstellar Mission, the spacecraft were slated to continue their journey into the unknown. Sagan convinced NASA to allow Voyager 1 to take one final series of images. On February 14, 1990, the spacecraft redirected its cameras toward the inner solar system and captured 60 last photos. One of these images, famously termed by Sagan as the pale blue dot, showed Earth from an astonishing distance of 3.8 billion miles. In the photo, Earth appears as a tiny, barely discernible against the vastness of space, illuminated by a faint glint of sunlight reflected off the camera's lens. We have gained a tremendous amount of knowledge about the planets and moons in our solar system, and it's thrilling to observe how unique and intriguing each one is, even those that are the farthest away. Voyager 1's journey beyond the heliosphere in August 2012 marked a significant milestone. By moving beyond the heliosphere, a vast region of charged particles emitted by the Sun, Voyager 1's notable achievement became widely recognized the following year when a study was published in the journal Science, detailing Voyager 1's groundbreaking discovery. The spacecraft's plasma wave instrument detected a powerful solar outburst between April 9 and May 22, 2013. This event caused electrons near Voyager 1 to oscillate, signaling that the spacecraft had entered a region of higher particle density than that found just inside the heliosphere. Initially, it might seem surprising that the electron density is greater in interstellar space than near the Sun. However, researchers clarified that the electron density at the edge of the heliosphere is significantly lower than at Earth's surface. By analyzing Voyager 1's data, researchers pinpointed the official departure date as August 25, 2012. This determination was based not only on electron oscillations but also on measurements of charged solar particles collected by the spacecraft on that notable day. Coincidentally, this was also the day that the famed Apollo 11 astronaut Neil Armstrong passed away. On this crucial date, Voyager 1 detected a remarkable thousand-fold decrease in solar particles and a 9% increase in galactic cosmic rays originating from outside the solar system. These discoveries highlight the dynamic and ever-evolving nature of our cosmic environment, showcasing the enormity and complexity of space exploration. Voyager 1 reached an incredible distance of 11.25 billion miles from the Sun, or about 121 astronomical units. At this juncture, NASA's Planetary Science Division was actively exploring the solar system using various methods, including flybys, orbiting, landing, roving, and sample return. The Voyager missions, as trailblazers of this approach, laid the groundwork for future exploration. The Voyager spacecraft played an essential role in surveying the universe and shaping our research priorities. By conducting flybys, these missions significantly advanced the success of planetary science. The concept of gravity assist, which involves using the mass of a planet or another celestial object to alter the speed and trajectory of a spacecraft, was crucial for the Voyager's successful exploration of the outer planets. Scientists and astronomers, in their quest to fully understand gravity assist, made an unexpected discovery about the vastness of outer space. Despite relying on gravity assist maneuvers for space navigation, the Voyager missions had another vital component: the Deep Space Network, DSN. This element functions like a cosmic telephone line that kept us connected with our daring Voyager probes as they ventured into the unknown. So, what exactly is the Deep Space Network? Although it may not be as glamorous as a spaceship, it is extraordinarily important. The DSN is akin to a vast network of radio antennas dispersed across the globe, from California to Spain to Australia. These enormous dishes, some as wide as 70 meters, act as space amplifiers, enabling us to communicate with spacecraft that are far out in space. What role does it play in the Voyager missions? The Voyager probes, equipped with cameras and sensors, were our eyes and ears in space. To interpret the data they sent back and provide them with instructions, a robust communication system was necessary, and that's where the DSN played a crucial role. When Voyager 1, traveling to the outer reaches of our solar system, sends a message back to Earth, it is a faint signal traveling incredibly fast through space. By the time it arrives on Earth, it's barely a murmur. But fear not. The DSN's massive antennas are ready to catch that faint signal. They lock onto Voyager's whisper and convert it into usable data for scientists. The Deep Space Network isn't just about receiving signals. It also sends commands. Missions like Voyager are dynamic, requiring scientists and engineers to adjust plans or issue instructions to the spacecraft. These commands are sent through the DSN, traveling through space to reach Voyager. It's like having a two-way conversation between Earth and the most distant human-made objects in space. One remarkable feature of the DSN is its constant operation, 24/7, always listening for those distant signals. It's more than just a collection of antennas. It's our crucial link to space. The DSN keeps the stories of the Voyager missions alive, even as the spacecraft journey far beyond our solar system, exploring the uncharted regions of interstellar space. The extended voyages of the Voyager spacecraft have encountered unforeseen challenges. Voyager 1, in particular, is outfitted with 3 onboard computers, including a flight data system responsible for gathering information from the spacecraft's scientific instruments. This data is then transmitted to mission control on Earth in binary code, a series of ones and zeros. Recently, however, Voyager 1's flight data system seems to be trapped in a loop, continually sending the same pattern of ones and zeros back to Earth. This issue was first observed on November 14th when the spacecraft's communications unit began behaving unpredictably. While Voyager 1 can still receive and execute commands from mission control, this problem means that no new scientific or engineering data is being transmitted back to Earth. NASA engineers have attempted to restart the flight data system, but so far, no usable data has been received. They are now working to identify the root cause of the issue before deciding on the next steps to resolve it. This process may take several weeks. Interestingly, this is not the first time Voyager 1 has faced issues with its flight data system. A similar problem occurred in 1981. However, the current issue does not appear to be related to any other glitches the spacecraft has experienced in recent years. As the Voyager probes encounter new obstacles, the mission team is relying on manuals written decades ago for guidance. These manuals, while thorough, could not have anticipated all the challenges the spacecraft would face as they continued their journey through the cosmos. The team is proceeding cautiously, carefully considering all potential ramifications before issuing any further commands to Voyager 1 to ensure that its operations are not unexpectedly disrupted. Voyager 1 is positioned so incredibly far away that it takes a staggering 22.5 hours for signals to travel from Earth to the spacecraft. And that's not all. It takes another 45 hours for the team to receive a response. Imagine waiting almost 2 days just to hear back from a spacecraft. As the Voyager twins continue their epic voyage through space, the team has had to make some tough decisions to keep them operational. They've begun turning off some instruments on these aging probes to conserve power and extend their missions. Along the way, both spacecraft have encountered unexpected issues, such as a 7-month period in 2020 when Voyager 2 lost communication with Earth. Fortunately, the team managed to restore contact in August using a clever technique that realigned the spacecraft's antenna. While the team remains optimistic about restoring the regular flow of data from Voyager 1, the true value of these missions lies in their longevity. Scientists are eager to study how particles and magnetic fields change as the probes travel farther from the heliosphere. However, this valuable dataset will be incomplete if Voyager 1 cannot send information back. The team has also been inventive in finding ways to extend the power supply on both spacecraft. Despite the challenges, the Voyager missions have far exceeded their original expectations, outlasting any other spacecraft in history. So, while the engineers work diligently to keep them operational, they also know that further challenges may arise. Despite their diminishing power, the voyages of these spacecraft are far from over.